Every time an IoT sensor sends a temperature reading or a GPS coordinate over a cellular network, that tiny packet of data passes through a sophisticated system of interconnected network elements before it reaches the cloud. That system is called the Evolved Packet Core, or EPC. By the end of this lesson, you'll understand exactly what the EPC is, what each of its major components does, and why this architecture matters when you're building or troubleshooting cellular IoT devices. The Evolved Packet Core is the backbone of every LTE network. It's the core network, the infrastructure that sits between the radio base stations your device connects to and the internet or private data networks your data needs to reach. Before LTE, cellular networks were built for voice calls first and data second. The EPC changed that completely. Introduced as part of the 3GPP Release 8 specification, the EPC is an all-IP, packet-switched architecture. That means there's no circuit-switched voice legacy baked in. Everything is data packets from the start. This matters for IoT because IoT devices almost never make voice calls. They send data. The EPC was designed from the ground up to handle exactly that kind of traffic efficiently. Let's walk through the major components of the EPC, starting from the device side and working our way toward the internet. This is the base station, the cell tower your IoT device communicates with over the air. The eNodeB handles the radio interface, managing everything from signal modulation to scheduling which devices get to transmit and when. In LTE, the eNodeB is smarter than its predecessors in 2G and 3G networks. It makes many of the radio resource decisions locally, which reduces latency and improves efficiency. The eNodeB connects to the core network through two separate interfaces. The S1-M-ME interface for control signaling, and the S1-U interface for user data. This separation is a fundamental design principle of LTE that we'll explore in detail in the next micro-module. The MME is the brain of the control plane. It handles all the signaling, is the management conversations, and between your device and the network. When your IoT device first powers on and tries to attach to the network, the MME is the component that authenticates it, verifies its SIM credentials with the HSS, and sets up the data session. The MME also manages handovers when a device moves from one cell to another, and it handles paging, the process of finding a device that's in an idle or power-saving state when the network needs to deliver data to it. For IoT specifically, the MME plays a critical role in supporting power-saving mode, PSM, and extended discontinuous reception, EDRX. These power-saving features rely on the MME tracking which devices are asleep for how long and when they'll wake up. The HSS is the master database of subscriber information. It stores your device's identity, the IMSI from the SIM, its authentication keys, its service profile, what it's allowed to do on the network, and its current location in the network. When the MME needs to authenticate a device, it queries the HSS. Think of the HSS as the network's identity and permissions database. The SGW is the first stop for user data, the actual payload your IoT device is sending. It acts as a local data anchor point, routing packets between the eNodeB and the PGW. When a device moves between cells, a handover, the SGW manages the data path switch so packets aren't lost during the transition. It also buffers downlink data when a device is in idle mode, waiting for the MME to page the device and wake it up. The PGW is where your device's data exits the cellular network and enters the internet or a private enterprise network. The PGW assigns your device its IP address, enforces quality of service policies, and handles charging and accounting. It's also where operators can apply traffic filtering, deep packet inspection, or route traffic through a private APN for security. Let's trace a simple IoT data transmission from start to finish. Your temperature sensor has a reading to report. The device's modem transmits the data over the air to the eNodeB. The eNode B forwards the data through the S1U interface to the SGW. The SGW routes it through the S5/S8 interface to the PGW. The PGW applies any QoS or filtering policies, then forwards the packet to the internet where it reaches your cloud platform. Meanwhile, all the signaling that set up this session, authentication, bearer establishment, security, flowed through a parallel path from the eNode B through S1-MME to the MME, and from the MME to the HSS for credential verification. The EPC core architecture includes the RAN, MME, SGW, and the device authentication flow. These components work as an integrated system, not isolated boxes. Understanding the EPC isn't just interesting. When you're debugging why a device can't attach to the network, you need to know whether the problem is at the radio level, eNode B, the signaling level, MME/HSS, or the data path, SGW/PGW. When you're choosing between a private APN and a public one, you're making a decision about PGW configuration. When you're optimizing battery life with PSM timers, you're configuring behavior that the MME manages. The EPC is the system you're working within every time you deploy a cellular IoT device. Knowing its components gives you the vocabulary and mental model to diagnose problems, ask the right questions, and make informed design decisions. Let's recap. The evolved packet core is the all-IP core network architecture that powers LTE. Its major components are the eNode B for radio access, the MME for control signaling, the HSS for subscriber identity, the SGW for local data routing, and the PGW for Internet Gateway and IP assignment. Data flows through the user plane from eNode B to SGW to PGW, while signaling flows through the control plane from eNode B to MME to HSS. This clean separation of concerns is what makes LTE efficient, scalable, and well-suited for IoT.